And first of the circuits are adders, and generally I'm sure you will have an idea. When we add 0 and 0, the answer is 0. When we add a 0 bit and 1, the answer will be 1. When we add 1 and 0, the answer will be 1. But when we add 1 and 1, the answer will be 0 because we cannot have 3. So the answer will be 0 here, but there will be a carry here. So this is a special case you have to keep in mind. When adding 1 and 1, the answer is 0 and we have a carry. And similarly, if we add 3, then actually we are adding 1 and 1, we're getting 0. And then with that we add another 1, then we get 1 here. And from here, the adding 1 and 1, we had got a carry, so we'll write it here. So this is how binary addition takes place. And first we'll discuss about half adders. Combinational circuit that performs the addition of 2 bits is called the half adder. So these 2 bits can be added by half adder, but for the 3 bits we got to have a full adder. Okay, so what are the inputs? X and Y, 2 inputs, and the possible combination is 0, 0, 0, 1, 1, 0 and 1, 1. And now, as we have seen from here, when we add 0 and 0, we get 0. When we add 0 and 1, this is the sum, S for sum, and this is for carry. So when add 1 and 0, we get 1 and no carry. But when we are adding 1 and 1, we get sum as 0 and there is a carry, just like this. Sum 0 and we have a carry. So sum 0 and we have a carry. So this is the truth table for half adder. And now let's see how we can implement this. So from here directly, you know how to write the equation. Like for sum, wherever there is 1, we'll write, we'll consider that value only. So here it is 1. So what is the input? X is 0, that means we'll write it is X dash, and Y is 1, so we'll write it 1. So X dash 1. Then there is another 1 at the sum, so we'll OR it with the positive sign, means OR, and this is when the input X is 1 and Y is 0, so that means it's X Y dash, so X Y dash. So this is the expression for the sum term. And now let's see the carry term. The carry is only 1 when both X and Y is 1, so X and Y is equal to C. So this is how we write the sum of product expression. And now to implement, you know, these are AND gates, X dash Y, that means actually X dash dot Y, and dot is for multiplication, or we'll do that with the adder. So if we have this input, first of all this one, let's say X dash input, and Y input, then the output of the adder is X dash Y, and this is going to the OR gate, so this is for OR gate. So we have implemented this part. The second part is X Y dash, so again we feed X from here and we feed Y dash from here. The output of the adder is X Y dash. This is also coming into the OR gate, and so the output of the OR gate will be this, or plus sign, the other one. So X Y dash or X dash Y. So this is how we implement the sum function. And for carry function, it will be simple adder. So carry is X into Y. So X input, Y input, and through an adder we get X into Y. So this is carry out. So this circuit will represent a half adder. Now, If you have learned XOR gate, I'm sure you will remember that XOR gate has the property that whenever one of the inputs are different, so like here one is 0, the other is 1. Here first one is 1 and the other is 0. So outputs are different, and then this can be implemented by an XOR gate. So this function, you see here also X dash and this is Y, that means 0 and 1, and here it is 1 and 0. So we can represent this by an XOR gate. So XOR gate has output x y dash plus x dash y, or we can also write it as x, and this is the symbol for XOR y. And we are feeding x and y to the XOR gate. And similarly, for the carry, we use an AND gate and we get the input x and y from here. And so this is the final answer. So I hope you have understood how to implement half address circuit. And this is symbolically we can represent, instead of drawing this whole thing, we can just represent it like this. Two inputs A and B and two outputs carry and sum. Now let's talk of the full adder. Now the full adder will add 3 binary bits, so just like here. So we'll have 3 inputs, and I am sure by now you have learned how to fill in these columns. So we have all the 8 possibilities, 2 raised to the power 3, so 8 possibilities we have written. And now to find this answer, we have to do the addition of all 3. So 0, 0, 0 added becomes 0. 0, 0, 1 will give you 1. 0, 1, 0 will give you 1. Now here there are 2 ones added. So 2 ones means 1 carry. So 1 carry and the sum is 0. And similarly here is 1. Here are 2 values. So again we get a carry and 0. 2 ones, so again we get a carry and 0. And 3 ones we get 1 and 1 as we had shown here. So this is the truth table for full adder. And now we can write their values in terms of the variables. So for sum here it is 1, 1, 1 and 1. So we'll have 4 values. And for this you can see 0 means x dash, 0 means y dash, and this is z. So x dash, y dash is z. Similarly, you can write all the 4 values from this table. Now we come to the carry. Now carry has 1 here and 1, 1, 1 here. So for this, you can see from here it is x dash, y, z. So we have written x dash, y, z. And similarly, you can write the other 3 values. And now we need to formalize this. So all are added with an plus sign, or that is OR sign. So for sum we can write S is equal to all these OR together, and similarly for carry all these OR together. So this is the formal equation. And now we'll take help of a K-map to simplify, because this may not be the simplified form. So it is better that we use K-map. So I hope you have learned how to draw a K-map. So we have 3 variables, so we'll write it x and y, z, 0, 1, 0, 0, 0, 1, 1, 0 and 1, 1. This is tricky. You have to remember that 0, 0, 0, 1, and then you go to the last one, 1, 0, and then come back for 1, 1. Okay. And now let's plot the sum. For sum we have 0, 0, 1, first one. So we go to this here, from here we get 0, and 0, 1, so we put a 1 here. Similarly, 0, 1, 0, 0, 1, 0 here, and this is 1, 0, 0, so this one is 1, 0, 0, and finally 1, 1, 1, so 1, 1 and 1. So these are the 4 ones we have put in the K map. Since we cannot further simplify these, therefore we'll write the answer just like this. But now let's see whether we can simplify the carry function. Same way we input the values of the carry functions. So we have a 1 at 0, 1, 1. So 0 and 1, 1. So we put a 1 here. And similarly we put these other 3 ones. And now you can see that you can combine these two. You can combine these two. And you can combine these two. So, and now you can write the equations of these two combinations. From here, if you look, we have x. So we write x. And from here, what is common is z. So we write z. So xz. And then you can write this two. Y and z common. So we write y and z. And then you can write for these two. So x common from this side and y from here, so it is xy. So this is a simplified form. So the carry function has been simplified. Instead of 4 gates, we are using 3 gates, and that too here the gates were 3 variable gates. Here we just using 2 variable gates. So that is the benefit of using K-map for final design. And now for the sum function, 3 variables, 3 variables, 3 variables. So we have 3 AND gates with all these variables written here. And then they are ORed with a 4 input OR gate. So this is the sum function. And same way we can implement the carry function with 2 AND gates, 2 variable AND gates. And they are ORed with a 3 input OR gate. So this is the implementation of full adder. And if you have to write it symbolically, we just write like this. We say full adder, 3 inputs A, B and carry, and the output is sum and carry out.